Okay. So first up, let's still talk about the schedule of the rest of our class and also the exam. Okay. So thank you for sending me your availability. So the make up class will be on this Friday. Okay. I send email to you. Okay. And tomorrow, today and tomorrow, we will have class here. Okay. Um, there are still two things I need to discuss with you. Okay, so first, uh, there is one class after the Thanksgiving holiday. Okay, yeah, the thing is, I think Orbit is not here. Okay, and also I feel I feel it's better to have that class also, by Microsoft Teams. So if you think that is fine. Yeah, the last class. Yeah, which originally scheduled on December the 1st, which is a Monday. Okay, so do you think it's okay to have that class also online? I mean through Microsoft Teams. Okay. Okay, okay. And also, yes, the time is also flexible, I think, for that class. Okay, so I'm going to ask you guys to send me also your availability for that class. So we need 1.5 hours. 1.5 hours. So oh, I don't know if you guys have any travel plans during the holidays. No travel plan. You just stay here. Oh, okay, okay. So then we are quite flexible. Okay. So then I will send you guys an email. Okay, about that. So you just reply with your availability. Okay, for that class. Okay. And also our final exam. Final exam. As I mentioned, December the 2nd to December the 8th. So which is the exam week. Okay. So I prefer putting our final exam on the 7th or 8th. So which is the 7th is a Monday and 8th is a Tuesday. Okay, so I'm also going to send you guys an email and you reply to me, I would say by this Thursday before the Thanksgiving holiday. So with your availability. So we need 2 hours for the final exam. Okay, and I will reserve the classroom. Okay, so that's our plan. Yes, for the last class and the final. Yes, yes. I will write that in the email. Okay, so you guys just reply me. Okay, okay. Any other questions? Okay, so now let's uh, continue with our lecture. Okay, continue with our lecture. Uh, so last time we talked about the hierarchical model. Hierarchical model. Um, so basically, the hierarchical model uh, at least it will contain two random variables, okay? And then those variables kind of depending on each other, so forms a hierarchical model, okay? So here we use the example of only two random variables, like here the insects will lay eggs, okay? And then out of those eggs, some will survive, okay? So those are two random variables depends on each other. So it forms this kind of model with this hierarchy. Okay, so like the survivors given the number of eggs laid, so which is y, so follows a binomial distribution. Okay, and the number of eggs follows the Poisson distribution, so forms this kind of hierarchical model. Okay, so the hierarchical model, so usually to find the marginal distribution is kind of complicated, the calculation. Okay, so therefore if we want to calculate some expected value or variance of the random variable of one random variable. Okay, so as I mentioned, so what we require here are two important formulas about the calculating the expectation and the variance in this hierarchical model. Okay, so on page 4, so we talked last time. Okay, so here the first formula is to calculate the marginal expectation of x. So we can do it in this way. So first we calculate the conditional expectation of x given y. Okay, and then second, we calculate the expectation of that conditional expectation, so which is a quantity depends on y. Okay, so this is the first important result. Okay, so second, about how to calculate the marginal variance of x. So it contains two terms. Okay, so and the two terms are kind of interchanging the calculation of expectation and variance. Okay, so the first term here is we first calculating the conditional variance of x given y. Okay, and then evaluating the expectation of that quantity. Okay, so second term we exchange the sign of variance out and expectation. So which means we first calculate the conditional expectation, okay, and then calculate the variance. Okay, so by those four formulas, so if we want to calculate the marginal expectation or variance of x in this hierarchical model, so we do not need to find out the marginal distribution of x, right? So we can directly use this conditional distribution to calculate based on the conditional expectation and variance to find out the marginal expectation and variance of x. Okay, so and we have seen this example. So last time, so about this one. So here, x given y follows this binomial distribution. Okay, and y follows the Poisson distribution. Okay, so by using those two formulas, okay, so first about the expectation of x, so we can write this marginal expectation, use this double expectation based on the conditional expectation of x given y. Okay, and then we know this conditional expectation of x given y, so which follows the binomial distribution. Okay, so which is easy to get. Okay, and then the second expectation, so outside these brackets, so that is about the expectation depending on y, depending on the marginal distribution of y. Okay, so which is a Poisson distribution. So we can easily find out those quantities. Okay, and also about the variance of x. So by the result, we can write it as a sum of those two terms. Okay, so first one, the conditional variance of x given y. Okay, so we know this conditional distribution of x given y is a binomial distribution. So its variance is also easy to find out. Okay, so we can write this like in this way. Okay, and then next we need to evaluate this expectation about y, this expectation evaluating on y. Okay, so we can see the expectation of y, which is a Poisson distribution, so which is lambda, so which is also easy to evaluate. Okay, and the second quantity, so similarly, inside the brackets, so that is about the conditional expectation of x given y, so which is binomial. Okay, and then this variance is about the variance evaluating on y. Okay, so we can take out this constant p. Okay, and we can see it depending on the variance of y, so which is also lambda. Okay, so basically by using those two formulas, okay, we do not need to find out the marginal distribution of x. Okay, so those two marginal expectation and variance of x, so we can write them as some equation depending on the conditional expectation and the conditional variance. Okay, and then those conditional expectation of x given y and the conditional variance of x given y, so they are easily to find based on this hierarchical model. Okay, so that's the basic idea here. Okay, so now let's see the next example. Okay, so this is also a hierarchical model. Okay, so here the model is like this. Okay, so here x is the, I think, number of successes. Okay, so the number of successes given the probability of a success p. So it follows this binomial distribution. Okay, so n, and the p is the probability of success. Okay, okay, and now we allow the p. This p also has a distribution. Okay, so which is a beta distribution. Okay, the beta distribution. Okay, so now let's find the EX and the variance of X. The EX and the variance of X. Okay, so still this is just the application of the two formulas, the two important results here. Okay, so first the expectation of X. So we can write this as the expectation of this conditional expectation of X given P. Okay, and then what is this conditional distribution of X given P? Binomial, right? And what is the mean of this binomial distribution? Yeah, n times the probability, np, right? So this is np here. Okay, and then here, remember p is also a random variable, right? So now this expectation becomes, we can take out the n out of the expectation, right? N is a constant here. So that is n multiply expectation of p. Okay, so we have calculated this. So p follows the beta distribution. Okay, so in chapter 3, we have calculated this, the expectation of a beta random variable, so which is alpha divided by alpha plus beta. Okay, so then this is the marginal expectation of x. Okay, and the next, the variance of x. So by the formula, so we can write this as a sum of two parts, right? Okay, so first part is the variance of the conditional expectation of x given p. Okay, the first part. Okay, so now let's look at the first part. Okay, so the variance of this conditional expectation of x given p. Okay, so we know the conditional expectation of x given p is a binomial. So this conditional expectation is np, right? So now we need to evaluate the variance of np. Okay, so by the property of the variance, so the constant n comes out of the variance need to be squared. Okay, so we have n squared multiply the variance of p. Okay, and then previously we have evaluated the variance of beta distribution. Okay, so which is this? Okay, so this is the variance of the beta distribution. So alpha beta divided by this. Okay, so this is the first part. Okay, second part, we need to evaluate this expectation of this conditional variance of x given p. Okay, so we know x given p is a binomial distribution. So its variance is n multiply p multiply 1 minus p. Okay, so then this is the variance of the conditional of the binomial distribution. Okay, so now we need to evaluate this expectation. Okay, so we take the n. We can take n out of this expectation. Okay, so then we need to evaluate this, the expectation of p multiply 1 minus p. Okay, so then this is, we have seen similar calculations in chapter 3. Okay, so here the p follows the beta distribution. Okay, so then by the definition of expectation, so this will be this quantity, so p multiply 1 minus p multiply the PDF of beta, right? So I will write the p here. This is the PDF of p, so which is a beta distribution. And then we need to integrate out over the support of P. So it's like this, right? Okay, so now we just plug in the form of the PDF of P. Okay, so which is this? So the density, the PDF of beta distribution. So that is, so the normalization constant is this. So the gamma function, gamma of alpha plus beta divided by gamma alpha and gamma beta, and multiply the kernel part. The kernel part of beta distribution is here, right? So P to the power of alpha minus 1, multiply 1 minus P to the power of beta minus 1. Okay, so this is the PDF of beta distribution. Okay, and then multiply this quantity. So P multiply 1 minus P. Okay, so similarly as in chapter 3, so we can use the kernel trick to find out this integral. Okay, so we put all the terms contains P together. Okay, so we put this together. Okay, so we can see this integrand is a kernel of another beta distribution, right? So this is the kernel of beta alpha plus 1 and beta plus 1. It's a kernel of this beta distribution. Okay, so then this will be this integral in terms of the kernel of this beta distribution. So that will be the inverse of the normalization constant of this beta PDF, so which is this one. Okay. Okay, so this should be plus sign. Okay, gamma function of this, the sum of the two parameters, so alpha plus 1 plus beta plus 1. Okay. Okay, and then by the property of the gamma function, okay, so we mentioned this, right? So if this gamma function, so evaluate as alpha plus 1, so this will be alpha multiply gamma alpha, right? So this gamma function has this inductive property, right? Okay, so then we can simplify this expression to this by cancel out some terms, by expand those terms. Elaborate a little. Oh, sorry, here. Right, so remember this is the property of the gamma function. So we have this inductive property. Okay, so then this term cancels out with this, so we have alpha here. This one cancels out with this, so we have beta here, right? So and this one, so we have cancel out with this, so we have alpha plus beta plus 1 here. Okay, so then this is the about this example. Okay, so again, so basically what we need to know about this part, the hierarchical models. So first is about the concept of this hierarchical model. It forms this depending structure, okay, with at least two random variables, okay, and then the key formulas to calculate the marginal expectation, okay, based on the conditional expectation and the conditional variance. So those two formulas. Okay, and as I mentioned, some about more detailed calculations about how to find out the marginal distribution of x. So those are not required in our course. So there is a specific field called hierarchical models or hierarchical modeling. So that field is more about the the more details about this hierarchical model. Okay, so and I think you will also learn something about this hierarchical model in Bayesian inference class. Okay, so actually Bayesian inference can be formed in these hierarchical models. Okay. Okay, so finally about this section, so let's turn to page 2 about the second node here on page 2. Okay, on page 2. So here in this second node, I just want to clarify one ambiguity in our textbook. Okay, so so basically the authors of our textbook, so they at the it was written about 20 years ago. Okay, at that time they think, so basically they think the hierarchical model and the mixture model or mixture distribution, they are the same. They have the same meaning. Okay, so they also call the hierarchical model as mixture distributions or mixture models. Okay, but nowadays, so these concepts have changed. Okay, so here I just want to clarify this concept of mixture distributions. Okay, so here the mixture distribution or mixture model. So usually it can be written as this form. Okay, so here the fx is our the PDF of the model. So it can be written as this linear summation of several different PDFs. So here I'm written as wrote as F1, F2, and Fk. So there are K. It's kind of mixture of K, different PDFs. So this mixture model is from those K different mixture of PDFs. Okay, so and then here the each P1, P2, and Pk. Okay, so here they are called the mixing weights or mixing probabilities. So that is the proportion of the the proportion of the values coming from each individual PDFs F1 to Fk. Okay, so one example is like I draw on this figure. So on the next page. Okay, so here the blue curve and this red curve. So there are two normal distributions with different mean and different variance. Okay, so this mixture distribution with some probability from the first, from the first normal distribution. Okay, and then also some proportion of data from the second normal distribution. Okay, so then together we will see this dashed curve, which represents the density of the mixture distribution of the two normal distributions. Okay, so this nowadays we call this type of model as a mixture model or mixture distributions. Okay, and then this is also a specific field, which is called mixture distribution or mixture models. Okay, so it's studied about this type of distributions. Okay, so and of course this is just for your information, not required in our course. Okay, and so far we have finished this section, hierarchical models. Okay, again, you need to understand the concept, just the concept of hierarchical model. And the required things are the two important formulas. Okay. Okay, so any questions so far? No.
Is there a benefit in the hierarchical model if one is a limiting distribution of the other?
One is the what limiting.
Limiting distribution.
So what do you mean by limiting distribution? Do you mean the like n goes to infinity?
You know, like how like when the binomial gets so large,
Uh-huh.
it gets to a certain point that you can use another distribution to.
Okay.
I think approximate would be the wrong word, but
Uh-huh.
something similar to that.
Well, I think I understand what you mean. Yeah. So if you're saying if this binomial distribution, say if the value of y, for example, becomes large, so this may converge to like Poisson distribution. Okay. Well, I think that's another thing actually. So when we talk about the limiting distribution, so here we are just talking about the the general way. So like here in this example is x will depend on y. Okay, so then it forms this hierarchical model. So like x depending on y, depends on y, and y follows some distribution. So like in this way. So what I mean is about talking about the limiting distribution seems a kind of different thing, different question here. Yeah. So here we are just talking about the general hierarchical model, like two random variables depends on each other. So it forms this hierarchical model. Okay. Okay. So now let's continue to the next part. The next part. Okay. So which is about the two important quantities that evaluating the relationship between two random variables. So which is covariance and correlation. Okay. So I think you probably know this definition in your introductory statistical course, right? The correlation. Yeah. So, but now let's give some more, details about this, and then see some, examples about how to calculate this covariance or the correlation. Okay. Okay. So the first definition is about the covariance of x and y. Okay. So which is defined in this way. Okay. So based on the expectation of x and y. Okay, so it's defined in this way. Okay, so to be more clear, I should put brackets here. Okay, so we first evaluate the quantity inside these brackets. Okay, and then evaluate the expectation of the quantity inside these brackets. So it's like this. Okay, so because here, let's just try to understand this covariance. So first, it's about gives us the relationship between two random variables. Okay, so it's like this. So first, it's a value. This is a value can take any values on the real line. Okay, from minus infinity to positive infinity. Okay, and then based on this definition, if we switch the order of x and y, so their covariance will be the same. Okay, so we can put the covariance of two random variables no matter of the order, about order of them. Okay, so and then what is the meaning of this value? Okay, so here the positive covariance is when small values of x tend to be observed with small values of y. Okay, so that means if this covariance is positive, okay, so then we will see the these small values. So let's say that we're talking about the relationship between x and y, right? So if their covariance is positive, okay, so then we will see, okay, if x is large, then y is also large. Okay, and x is small, then y is also small. So this is like the in the definition, by the definition of covariance. Okay, and then if this covariance is negative, okay, so that means x and y tend to be in different direction. Okay, so if x is large, so then y tend to be small. Okay, so if x is small, then y tend to be large. So that is the case when this covariance is negative. Okay, so that is the meaning of this covariance. Okay, so here the covariance can be any value on the real line. Okay, so then the next quantity, correlation, is defined as a like a standardized version of the covariance. Okay, so we just standardize this covariance of x and y by their standard deviations. Okay, so here the sigma x and sigma y, so they are standard deviations. So which means square root of variance. Okay, standard deviations of x and y. Okay, so now we define this correlation as the covariance of x and y divided by their standard deviations. So which kind of standardize this quantity, the covariance? Okay, and now we make this new quantity, the correlation between x and y, in this range from -1 to +1. Now make this in this range. Okay, so it's kind of standardize this covariance to make it fall in this range. Yeah. Okay. And the meaning of the correlation is quite similar to uh, covariance to the covariance. Okay. So uh, here the correlation is in this range -1 and +1. Okay. And if this correlation tends to be 1, okay, approximate, goes to close to 1. So that means the two random variables x and y, so they may have like a linear relationship. This say if this is x, this is y, x and y. Okay, so if this row the correlation is close to 1, so that means they have the x and y almost have this linear relationship. And then also they are in the same direction. So that means if x is increasing, y is also increasing. Okay, and then if this correlation goes to -1, okay, so that means they also have a linear relationship, but their directions are different. So like x and y. Okay, so that means if x is increasing, y will decrease. Okay, so that is the meaning of this correlation. Okay, so like here I mentioned, so if this row is -1, so that means there is a perfect linear relationship between x and y. And then for -1, so that is a perfect negative linear relationship. Okay, so that means x and y will be, given by the relationship of x, y will be given like in this line. So they are on this negative direction. Okay, and on the other hand, if rho is 1, so that implies this linear positive linear relationship between x and y. So like in this direction. Okay, so and other values between -1 and +1. So that implies the relationship between x and y will be in the middle of those two extreme cases. Okay, so that's the meaning about the correlation coefficient. So I would say, so and also to be rigorous, this is actually called a Pearson, named by this statistician first developed this quantity. So Pearson, Carl Pearson, so who is a British statistician. So this is called the Pearson correlation coefficient. Okay, okay. So that is the definition of correlation coefficient. Okay, so which is a standardized version of covariance, gives us the linear relationship between x and y. Okay, so the next one just gives us a convenient formula, a more convenient formula to calculate the covariance between x and y. Okay, so I will leave the more detailed calculation for you guys to verify this. Okay, so based on this, the definition, so we can show this covariance can be also written in this way. Okay, so that is the expectation of the products of xy, okay, minus the products of their individual expectations. Okay, so this is an alternative formula to calculate the covariance between x and y. Okay, so on the next theorem, okay, so that is about the if x and y are independent. Okay, x and y are independent. Okay, it's here. So then their covariance and the correlation coefficient are both 0. Okay, x and y are independent. Okay, so can you directly see this through this formula, through the formula of covariance of x and y? Okay, so I think this is now you need to see this quickly. Okay, so x and y are independent, right? So remember by the property of independence. So we have this, right? The expectation of x, y. This the products of function of only x and y. So it can be written as the products of the expectation of individual functions of x and y. So like this, right? So then this minus this, so will be 0, right? So then the covariance is 0, so of course the correlation coefficient is also 0. Okay, so that's an important result. Okay, if x and y are independent, so their covariance and the correlation is 0. Okay, but how about the other way? So if their covariance and the correlation are 0, so are they independent, x and y? Okay, so the answer is no. Okay, which means the if covariance or correlation is 0, so does not imply x and y are independent. So we do not have that result. Okay, so here as a brief explanation here. So basically the covariance and the correlation measures the linear relationship. Okay, this linear relationship between x and y. Okay, so we will see a counter example soon. So that in that example, so x and y, they have a nonlinear relationship, so nonlinear dependency. Okay, and their covariance or correlation is, in that case, is almost 0. But they are depending on each other through a nonlinear relationship. Okay, so we will see example soon. Okay, and so the next two theorems. So let's look at some properties of the covariance and the correlation. Okay, so first one. So here x and y. So they are any2 random variables. Any2 random variables. And then here a and b are any2 constants. Any2 constants. Okay. So then we have this about the variance of ax plus by. Okay. So ax plus by. So it has 3 terms. Okay. So first term, so that is the a square multiplied variance of x. Okay, so that is about the variance related to variance of x. Okay, so second term, so that is b square multiplies variance of y. Okay, so that is related to the variance of y. Okay, and then there is a third term here. Okay, so we have 2 multiply a multiply b. Okay, and multiply the covariance between x and y. Okay, so if x and y are independent, okay, so then the third term disappears. Okay, so then we will have only this a square multiplies variance of x plus b squares multiplies variance of y. Okay, so this is a formula about this. So remember in chapter 3, actually we talk about this. So this is a linear transformation or linear sum, okay, in this form, okay. And then in chapter 3, I think we mentioned this, the expectation of this. So this is straightforward. So this will be just we take the expectation on the two individual random variables. So that this will be just like this: a multiply ex plus b multiply ey. Okay, so it's like this. Okay, but here we are talking about the variance of this. So remember, in the variance, so except in addition to the first two terms, we also have this covariance term. Okay, we also have this covariance term. Okay, and the proof I will leave for you guys to read in the textbook. Okay, so we will just go over those results because of the time. Okay, so next one. So this theorem, we probably already seen this in the introductory statistics class. So first, the correlation coefficient is between -1 and the +1. Okay, and the meaning I already explained. So it's basically the sign of these correlation coefficients represents the direction of the x and y. Okay, okay. So second one is so if this correlation coefficient is 1, so here the absolute value of it is 1, so means either +1 or -1, right? So this if and only if there exist numbers a which is not 0 and b such that this probability of y equals ax plus b is 1. Okay, so in other words, this y will be equals ax plus b. Okay, so which means a perfect line, perfect linear relationship between x and y. Okay. So as I mentioned, so if this rho is +1, so that means this a constant a, we call it the slope, right? In algebra, it's this slope a is positive. Okay, so if rho is 1, okay, and then if rho is -1, so then this slope a is negative. Okay, and then for values of rho between -1 and +1, so they are kind of in the middle of those two cases. Okay, so those are the properties of the covariance and the correlation coefficient. Okay, so now let's see one example, a counter example. So here the x and y, so they are strongly related through a nonlinear relationship, but their covariance is 0. Okay, for more details, I will leave you guys to read this example. Okay, so here I will just explain this example. Okay, so in this example, the y relationship between x and y, so it's almost like this. So y is about equals the square of x. Okay, you will see some more details. So this is roughly about the case here. Okay, so y is about the square of x. Okay, and then you will see. So based on the numbers given in the textbook. Okay, so you can find out the covariance between x and y. So it's almost 0. Okay, so it's almost 0. Okay, but however here x and y they have a strong relationship. This strong nonlinear relationship. So we'll see like this. Okay, but their covariance or correlation is almost 0. Okay, so then this is a counterexample. So shows even if the covariance or correlation is 0, so that does not imply x and y are independent. Okay, Okay, so that's about the properties of the covariance and correlation. Okay, so now let's see example. So this example, I want to demonstrate some calculations about the covariance and correlation between x and y. Okay, so here we have this x and y, so a bivariate random variable with this joint PDF. Okay, so fxy is 1. Okay, and the support is here. The support is given here. Okay, so and we have some question here. So first, let's try to find the marginal PDF of x and y. Okay, and the means and the variances of x and y. Okay, and last one, the covariance and correlation of x and y. Okay, so remember working on those this bivariate problem. So the first step is we need to draw some sketch plot about the support of x and y. Okay, so I have this sketch here. Okay, so here this line is x equals y. Okay, this line, the diagonal here is x equals y. Okay, and then this line is y equals x plus 1. Okay, so this is based on the support of x and y. Okay, so we always need to be careful about the support. Okay, so which is here. Okay, so then we can see x is between 0 and 1, from 0 and 1, from here to here. Okay, and y is between x plus x and x plus 1. Okay, so y is between the region of the two lines. Okay, so then this shaded area is the support of x and y, of the joint distribution of x and y. So this area. Okay, so then now we can work on the based on this. So we can work on those questions. Okay, so first to find out the marginal PDFs of x and y. Okay, so the marginals will be the joint. We need to integrate out the other random variable, right? So to find out the marginal of x, so we need to integrate out y. Okay, so which is here. Okay, so here the region, the support of y, so which is from this line. So that is y equals x to this line. So we need to integrate out y. So we need to look at the vertically this way, right? So we need to integrate out from x to x plus 1. So this is the range of this integral. Okay, from this line to this line. Okay, so then this is from x to x plus 1. Okay, and then the calculation is easy, so which is this. Okay, so the marginal distribution of x is just 1. Okay, so the support of this is from 0 to 1. Okay, so second, to find out the marginal PDF of y, the marginal PDF of y. Okay, so we need to integrate out x. Okay, but now we need to pay attention to the region of this integral. Okay, so to integrate out x, so we need to look at horizontally. We need to look at this way, right? So here in this region, actually this region contains two parts. Okay, so for the first part, this lower part, okay, so the region for this integral is from this line to this line, right? So then this is from y equals to 0. We need to integrate our x. So this line is x equals to 0, right? And this line is x equals to y. on this region, on region 1, in region 1 here. Okay, so then we have this. Okay, okay, and then on this second region, so the limit of the range of this integration is different for the two regions. Okay, so on this region 2, so the two limits of the integration is from this line to this line, right? So then this is the integration need to be evaluated from this line is y minus 1 unto this line. So this is x equals 1 from this line to this line. Okay, so you know what I mean, right? Yeah, based on this plot. So the limit of the integral for the integral, so they are different on those two regions. Okay, so then we need to write this integral as these two parts for those two parts. Okay. Okay, so then this is about the marginal PDFs of x and y. Okay, the next part, find the means and the variances of x and y. Okay, so this is easy to calculate given the marginal PDFs. Okay, so then I will directly give you the answer here. Okay, so first the expectation of x and the variance of x. Okay, so those are the expectation and the variance of x. Okay, so to calculate the expectation and variance of y, okay, so we need to pay attention to this, the form of the PDFs of y. It contains these two parts. Okay, so then the expectation of y will be the y. So multiply the PDF of y. So this is for the first part. Okay, it will be a sum of second parts. Okay, the sum of those two parts. So corresponding to the two regions. Okay. Yeah, so this is the definition of the expectation. Okay, but why the PDF of y contains those two parts? So it's given like this. So we need to write this as a sum of those two parts. Okay, so which is 1. So the final result is 1. Okay, and then same thing for the variance. Okay, when we evaluate this variance, to calculate the expectation of y squared. Okay, so we also need to write this as the sum of two parts. Okay, so the detailed calculation I will leave for you guys. Okay, so which is 1/6. Okay, and then the last question is to find out the covariance and correlation of x and y. Okay, so for the covariance, we will use this formula. Okay, so here we already know EX, EY. Okay, so we only need to evaluate this expectation of X, Y. Okay, so then to find out this expectation, so we will use the definition. Okay, so which is XY multiply the joint PDF. XY multiply the joint PDF of XY. Okay, so the joint PDF of xy, so which is 1. Okay, so then we will need to evaluate this double integral. Okay, so we have seen this before, right? So we can either first integrate out x or integrate out y. So it doesn't matter here. Okay, so here I will first integrate out y. Okay, integrate out y. Okay, so again, based on this plot, So we will need to find out the range of the integration, okay, the limits of the integration. So to integrate out y, so that is on this, we need to look at vertically. We need to look at vertically, right? So that is from y equals x to y equals x plus 1. Okay, so we have this from x to x plus 1. Okay, and then the limit for x, so that is from 0, from this line to this line, from 0 to 1. Okay, so then the rest thing is we just need to evaluate this double integral. Okay, so I assume you guys are familiar with this. Okay, so we have this here. Okay, so then we have everything to calculate the covariance of x and y. Okay, so okay, and then the correlation coefficient will be the covariance divided by the standard deviations of x and y. Okay, so then we can directly, we have everything here. Okay, so that's about this example. Okay, so the last part of this section. So let's look at another important distribution. Okay, but this distribution contains two random variables. Okay, so which is called the bivariate normal distribution. The bivariate normal distribution. Okay, so this is the last concept in this part. Okay, so here we have the two random variables x and y. So they forms a bivariate random vector. Okay, so and this is the form of the bivariate normal distribution, the PDF of the bivariate normal distribution. Okay, so basically it contains five parameters. Five parameters. Okay, so the first two are mu x and mu y. So which are the two means corresponding to x and y. Okay. Okay, and the next two are sigma square x and sigma square y. Okay, so they are the two variances correspond to x and y. Okay, and the last parameter is the correlation coefficient between x and y. So it has those five parameters. Okay, and then let's look at the form of this PDF. Look at the form of this PDF. Okay, so we can see it is similar to the univariate normal. Okay, so this constant part, so it contains the 2 pi, okay, sigma x, sigma y. Okay, the only difference is here we have this 1 minus rho square. So here the correlation comes here. Okay, and then the exponential part. So basically, the exponential part is also a quadratic function of x and y, has this square here, the quadratic form. Okay, so here this one, I mean those two terms contains only x and y, so they are similar to the univariate normal. Okay, so that is x minus mu, okay, divided by sigma x and the square. Okay, so the only difference here is also it contains this interaction term. Okay, contains both x and y, and also the correlation coefficient. Okay, so this is the we call this PDF as bivariate normal PDF. Okay, so alternatively, so we can write this bivariate normal PDF in a more general way. Okay, so now we define this matrix. Okay, so which sigma, so which is called the variance covariance matrix of the bivariate normal distribution. So this sigma is called variance and the covariance matrix of the bivariate normal distribution. Okay, so on this matrix, so on this diagonal, so which are sigma x squared and sigma y squared, so which are the variances correspond to x and y. Okay, and on the off diagonal, so that is rho multiply sigma x, sigma y. Okay, so then what is this quantity? The covariance between, right? So this is the covariance between x and y. So the two off diagonal elements, they are the same, right? Rho multiply x, sigma x, sigma y. Okay, so remember this correlation coefficient, so it equals covariance of x and y divided by sigma x, sigma y, right? So then rho multiply sigma x, sigma y will be the covariance between x and y. Okay, so that is why this sigma is called variance covariance matrix of the bivariate normal distribution. Okay, so if we write define this covariance matrix, formally it's called variance covariance matrix. Okay, but sometimes we can just call it covariance matrix. Simply call it. Okay, after we define this covariance matrix, okay, so after some linear algebra, so we can write this in a more compact form. Okay, so it's like this. Okay, so now we can see this part, the normalization constant part. So it's actually similar to the univariate normal. But now we replace the variance with this covariance matrix sigma. Okay, so if you compare this with the univariate normal, okay, and then inside this exponential function, okay, we can also write this as a quadratic form. Okay, involves this sigma covariance matrix here. Okay. Okay, and then there are some important properties of this bivariate normal distribution. Okay, and here I will just go over them and explain. Okay, and more detailed verifications I will leave for you guys. Okay, so first one, the marginal distributions of x and y are two individual normal distributions. So the marginal distributions, okay, and then their mean and the variance are exactly the quantity in this bivariate normal distribution. So here the mu x and mu y are the means of x and y for the marginal distributions of x and y. Okay, and then sigma x squared and sigma y squared. So they are the corresponding variances of the marginal distributions of x and y. Okay, so they are the marginal distributions are also normal. Okay, and then by the name of this correlation, so the correlation coefficient between x and y is this rho as defined in this bivariate normal PDF. Okay, so and then the next one, Okay, so here for any constants A and B, okay, so the distribution of this linear sum of x and y, so they will be the distribution of this linear transformation of x and y, so which is also a normal distribution, also a normal distribution. Okay, and then what are the mean and the variance? Okay, so this is actually the property of expectation and variance we already mentioned. Okay, so here the mean will just be the linear sum of the mean of x and y. Okay, and then the variance, so we also has these three terms. Okay, first one is this a square sigma x squared plus b squared sigma y squared. Okay, and the third term will contains the covariance here. Okay, so that is 2ab multiply the covariance between x and y. So we can write this covariance as correlation multiply sigma x sigma y. Okay, so linear transformations of I would say linear sum of two normal is also a normal distribution. Okay, so the next one, so the conditional distribution of x given y or y given x, so are also two normal distributions. Okay, so the PDF of x given y is this. Okay, so here that is mu x, the mean is mu x plus some, we will say some quantity involves mu y. Okay, and then the variance will be sigma x squared multiply 1 minus rho squared. Okay, and then the last quantity is, okay, only for this bivariate normal distribution, it has this property. Okay, so that is if their correlation coefficient rho is 0, so then they are independent. Okay, so remember we mentioned the previous on the previous page, so we mentioned, okay, so that is the independence implies this covariance is 0, right? But we say the other way is not true, right? So covariance 0 does not mean x and y are independent. Okay, so we mentioned in this counterexample. Okay, but the other way is only true for this bivariate normal distribution. So here, if rho is 0, x and y are independent. Okay, for this bivariate normal distribution. Okay, so I think those properties I explained. Okay, so now I will ask you guys this: how can you think about how to prove this? I mean, formally prove this. Okay, here I will just talk about some the ideas and leave the calculation, as an exercise for you guys. Okay, so first about the marginal distribution of x and y are normal. Okay, so for this one, we can use the property of the marginal distribution. Okay, so we can, because we have the form of this joint PDF of x and y, right? So then to find out the marginal distribution, so we can integrate out the joint. Okay, although the calculation is a little bit complicated, but it is doable, I think. Yeah, so to do that, so you will see the form of the PDF, marginal PDF of x, y are exactly this normal distribution. Okay, so then we can prove this one. Okay, and the correlation, so this is easy to see. Yeah, this is just based on the definition. Okay, or you can evaluate based on the form of this joint PDF of bivariate normal. So you can evaluate this quantity, the EXY minus EX multiply EY, right? So this is the covariance. Okay, so now we are given this joint PDF, so we can find out those quantities. Okay, so you can verify this. Okay, and then the third property, so that is the directly application of the property of the expectation and the variance. So we just mentioned. Okay, so the fourth property here, the conditional distribution of x given y. Okay, so here the conditional distribution of x given y. So that will be the joint divided by the marginal. Okay, again, you can use this to find out this is also a normal distribution. Okay, so and the last one, so why they are rho is 0 implies x and y are independent. Okay, so that is based on the form of this joint PDF. Okay, so if rho is 0, so actually, remember how can we show x and y are independent? So we have the definition and also the factorization theorem. So that is the joint PDF can be factorized as the products of the two individual marginal PDFs. Okay, so I will leave you guys to verify this. Okay. Okay, so that's okay. I forgot one thing. We still have let's see the last page. Okay, this some plots about the property of this bivariate normal distribution. Okay, that's the last thing. Okay, let's use 1 minute. Okay, so here on the left columns, those this gives us which is the density plot for the bivariate normal. Okay, or the PDF. So we say the plot of the PDF. Okay, but now we have the two random variables x and y. So the density plot will, will be a 3-dimensional plot like this. Okay, and then the head of this, this like a volcano here. Okay, the height of this volcano will be the density of this bivariate normal. Okay, so fxy. So on this axis, on the vertical axis, the height will be the density. Okay, so here we have six different bivariate normal distributions with different variance and correlation here. So we have 6 of them. Okay, so another plot to visualize this bivariate normal is like I draw here. So which is called contour, this contour plot. Okay, so what is the meaning of this contour plot? Okay, so on this 3-dimensional density plot, okay, so basically we write a line connects the points has the same density. Okay, and then project those lines on this 2-dimensional space. Okay, so then we will have this all those circles or ellipses. Okay, so the points on the same projected on the same circles or ellipse here, so they will have the same density. Okay, so then we will have this kind of 2-dimensional plots shows the points that has the same density, so which is called contour plots here. Okay, 2-dimensional on x and y. Okay, so what we can see from those examples here with different, so the first 2 examples are correlation rho is 0. Okay, so on the second row, so rho is positive. Okay, And here, those two examples, so the row correlation are negative. Yeah, so based on this contour plot, if the correlation is 0, so the main axis of those ellipses in this contour plot will be perpendicular to the, no, sorry, not perpendicular. I would say the main axis, so of this, you know what I mean, right? The main axis of this of these ellipses will be the x, will be one of the axes. So either this y-axis or x-axis, so like this. Okay, for this one, the main axis of those ellipses are this x-axis. Okay, so it's vertical, vertical or perpendicular to the main axis or x or y. Okay, but if x and y they are correlated, so then the main axis of those ellipses, they will have some angle with with y-axis or x-axis. Okay, here, like in this second row here, those two examples. So if their correlation are positive, so we will see the axis of those ellipses goes in this way, like it goes in this positive way. Okay, goes up like this way. And then on the other hand, so if those correlations are negative, so we will see the main axis of those ellipses will go in this way. So it goes down in this way. So this indicates a negative relationship between x and y. Okay, so those are the properties of the plot of the bivariate normal. Okay, based on the contour plot, so we can tell the correlation coefficient between x and y. Okay, so that's all for today. Okay, so we will continue tomorrow. Okay. And I think I print out the next